All right, so for 2.7, we're going to talk about some graphing techniques. Basically, we're going to look at transformations. So the first thing we're going to talk about is stretching and shrinking. So some of your numbers are going to get bigger and smaller. So first off, let's look at this first example here. So we have g of x equals 2 times the absolute value of x. So what I want you to do is we're going to make a table. And we're going to look at, the absolute value of x. And then we're going to have 2 times the absolute value of x. So when you have a number outside of the function, that is going to do something to the y-axis, okay? So when it is outside the function, it's going to affect your y-axis. So if it was inside the function, then it would affect the x-axis. So let's choose some numbers. Let's go negatives to positives. And then the absolute value of negative 2 is 2. The absolute value of negative 1 is 1. The absolute value of 0 is 0. The absolute value of 1 is 1, and the absolute value of 2 is 2. So now let's plot those points and see what that graph looks like. So negative 2, 2, negative 1, 1, 0, 0, 1, 1, and 2, 2. So we've got a graph that looks something along those lines. Now it says to take and multiply by 2. So you're going to multiply this number by 2. So 2 times 2 is 4. 1 times 2 is 2. 0 times 2 is 0. 1 times 2 is 2. And 2 times 2 is 4. So now, let me make that skinny so we can use it. Now your points are negative 2, 4. So negative 2, 4. Negative 1, 2. 0, 0, 1, 2, and 2, 4. And now your graph looks like this. So what you notice is, even though the graph is skinnier, this is considered a vertical stretch. And it's considered a vertical stretch because notice, just look at the numbers. If you compare your two y values, using this x value, your y value got bigger, so it's stretched. So to use the same x value, but your y values get bigger, is considered a stretch. Now, if you look over here at this one, so doing the same thing, we're going to do x, absolute value of x, and 1/2 of the absolute value of x. So this time, since we're going to be dividing by 2, I'm only going to choose numbers that are divisible by 2. So I'm going to do negative 4, negative 2, 0, 2, and 4. So this would be 4, 2, 0, 2, 4, because the absolute value of anything negative is positive. Now you're going to take half of that absolute value of x. So half of 4 is 2. Half of 2 is 1. Half of 0 is still 0. Half of 2 is 1, and half of 4 is 2. So now I'm going to plot these 3 points. So starting with my original, so we got negative 4, 4, negative 2, 2, 0, 2, 2, and 4, 4. All right, so next I'm going to plot this. So half of the absolute value of x. So now I've got negative 4 and 2. So negative 4 and 2. Negative 2 and 1. 0, 0. 2, 1. 2, 1. And 4, 2. 4, 2. And now we have that graph. Oh, that's a terrible line. But as you see, the graph looks bigger, but yet if you look at your y values, they got smaller. So this is considered a vertical shrink. Every time I say the word shrink, I think of shrinky dinks. So when your value in front, we'll call this A. So if you have a function and you multiply the function, actually let me use different letters. I don't like those. Let's say that you've got y equals f of x. Y equals a times f of x. If this letter A is greater than 1, it's a stretch. And if it's less than 1, so if it's between 0 and 1, it is a shrink. And it's because your y values are getting smaller or larger is what's considered a shrink or a stretch. Now this one, notice that it is inside of your absolute value. So now what we're going to do is we're going to have some x values, and we have the absolute value of x. And then we're going to do the absolute value of 2x. So now instead of having y equals f of x, now it's y equals f of 2x. So this is going to, it's going to look similar to the others, but I want you to see, I'm going to use the -2, the -1, 0, 1, and 2. So this is 2, 1, 0, 1, 2. So that's the same, absolute value of x. Now you've got 2 times x. So now 2 times -2 is -4, and the absolute value of -4 is 4. -1 times 2 is -2, and the absolute value of -2 is 2. This is going to be 0. 2 times 1 is 2, the absolute value of 2 is still 2. And 2 times 2 is 4, the absolute value of 4 is still 4. So even though it looks like it looks like this one, where it was on the outside, it does have a little bit different effect. All right, so we're going to have -2, 4, -1, 2, 0, 1, 2, and 2, 4. All right, it says, how does each graph in example 1 compare to the graph of the basic function? So here we notice that our y values got bigger. Here we noticed our y values got smaller. Here the y values got bigger because it was using the 2 is kind of what kept it doing the same thing. If I had focused on what if I did the absolute value of x and then another table with the absolute value of 2x. Okay, so I want us to think about this. What if I chose the y values? Let's say I wanted the y values to stay the same. What x value would you use? So if it's a 4, then this would be -4. If this is 2, it would be -2, 0, 0, 2, 4. Now if 2x is equal to 4, what would x be? Well, 2x equals 4, so x could be positive or -2. If 2x is equal to 2, x could be positive or -1. And if it's 0, it's going to be 0. So notice now, because I know it kind of seems like we did the same thing, but notice our y values stayed the same. But notice what happened to our x values. Our x values got smaller. So this time, if I were to graph the original, So I'm going to enlarge this a little bit. So if I graph the original, negative 4, 4, negative 2, 2, 0, 0, 2, 4, 4, 4. Notice for the y values to stay the same, your x values got bigger. So if you're looking at your x values. So keep that in mind as we move to the next part. Here, if A is between, then that's going to be, because I don't want to explain too much. So here, whenever the A is on the outside of the function, it's going to be vertical. It's going to deal with your y values. When it's inside with the x, this is going to affect your horizontal or your x values. Okay, so this is going to be a horizontal. So since this was a 2, this is going to be a horizontal stretch. Okay, because notice the x values got bigger. So since we're dealing with x values and they're getting bigger, your x values are stretching. I knew I was going to do that. This is greater than 1. Here we had the same output and we needed smaller x values. All right, a vertical stretch. So suppose that your A, so remember I said that y is a times f of x, okay? So if A is greater than 0 and you have some point xy that lies on your graph of your original function, then if you take this very point right here, if you leave x alone but you multiply the y value by A, then you're going to get this function. So if A is greater than 1, this is going to be that vertical stretch. And then if A is between, kind of like what I was saying, shrink. So this is going to be a vertical shrink or compression, depending on the term of the textbook. You're smushing it. You're making it smaller. Now horizontal, let me go back here. So now, if the A is between 0 and 1, so if your A is a fraction, then the graph is going to be I said this backwards, it was greater than 1. So since my A was greater than 1, this is a horizontal shrink. Everything's backwards when it deals with the x-axis. So if A is greater than 1, your x values will be smaller. And when A is between 0 and 1, this is a horizontal stretch. And I made myself a note to read to you. So think of it as the backwards rule, okay? I'm going to add a page here because I want you to see this. So let's go back here and let's look at this example. So we have g of x is the negative square root of x. So what we're going to do is we're going to create a table, x and the square root of x, all right? So we're going to graph you have to graph the original before you make any changes. And then we're going to make a table with x and negative square root of x. And we're going to come up with a rule that kind of goes with it. So since it is square root, you cannot use negative numbers. So we're going to go 0, 1, 4, and 9. Okay? The square root of 0 is 0. The square root of 1 is 1. The square root of 4 is plus or minus 2. And the square root of 9 is plus or minus 3. All right. So let's just graph 0, 0. We got 1, 1. Actually, let's just keep these on this end positive. So we got 2 and 3. And then we got when x is 4, we got 2. And when x is 9, we got 1, 2, 3. So your graph is going to look like this. Okay? Now, if I use 0, 1, 4, and 9, now I've got a negative out here. So the square root of 0 is 0, negative 0 is still 0. The square root of 1 is 1, negative 1. The square root of 4 is 2, negative 2. The square root of 9 is 3, so we'll put a negative. So now we got 0, 0, 1, negative 1, 4, 4, negative 2, and 9, 1, 2, negative 3. Now we've got this graph. Now notice that they are identical, except it's a reflection, where this is where you place the mirror, and it's the same on both sides. This is a vertical reflection because the negative sign is in front. So this is like saying f of x. So if our f of x is the square root of x, then what we did is we said g of x is negative f of x. So it's out front, kind of like the 2 was in front. So we said it changed vertically, changed your y values. So here, your x values stayed the same, but your y values changed. So we went from our points to the y values being negative. So this is a vertical reflection. So we reflect over the x-axis. Means your y values change. All right, now let's look at example B. So we have the square root of negative x. So I want you to see the difference between when the negative sign is in front, so that means the whole function is negative, and when it's paired inside with the x, that means just the x is negative instead of the whole thing. So we're going to do our table again. So we have x, and then we have the square root of x. And then we have the square root of negative x. All right, so now this time we can use negative values for our x, because when you plug a negative in here, a negative into this x here, you get negative, negative, which makes it positive. So then you can take the square root. So we're going to look at negative 4, negative 1, 0, 1, and 4. So if I take the square root of negative 4, this one is undefined because we're not able to do that. The square root of negative 1 is also undefined because you cannot take the square root of a negative number. The square root of 0 is 0, the square root of 1 is 1, the square root of 4 is 2. And then now if I plug in a negative 4, the square root of negative 4 is the square root of 4, which is 2. Same thing, the square root of negative 1, the square root of negative 1 is 1, and the square root of 0 is still 0. Now if I plug in a positive 1, now this one is undefined, and if I plug in a 4, now it's negative 4, so it's undefined here. So now when we plot both of these, so we'll plot the first, just the regular square root first. I'm going to slide this over and enlarge it a little bit. So I can't plot negative 4 or negative 1 because it's undefined, but I can plot 0, 0. I can plot 1, 1, and I can plot 4, 2. So I can see that this is our f of x, and then I'm going to plot the other one. So now I've got negative 4, 2, negative 1, 1, 0, 0, and then the rest is undefined. So now I have the curve that goes this way. So now we have our h of x. So now you see, instead of like the previous problem where it reflected this way, now it's reflecting that way. So now our x values changed and our y, well, I don't know what just happened there, and our y values stayed the same. So we went from positive x's to negative x's, but the y values stayed the same. So this is your horizontal reflection. Or reflecting over the y-axis. And this is, so when you reflect over the x-axis, the y values change. And when you reflect over the y-axis, the x values change. So if you can remember those rules, it'll help you when you are graphing other graphs that might not be as familiar. All right, so think of this. If A is big, okay, meaning greater than 1, smaller x values are needed to reach the same output. So that's where I was saying if A is small, meaning between 0 and 1, larger x values are needed to reach the same output. All right. So let's see. All right, here we go. So I don't know what happened there. All right. So how does each graph in example 2 compare to the graph of the basic function? F of x equals the square root of x. When we did g of x was negative f of x. It was a reflection over the x-axis. And the rule was the x and the y became x negative y. And then when we did f of x to h of x, it was a reflection over the y-axis. And the rule was the x is changed and the y stayed the same. All right. So the graph of, so we have negative x, so it's going to kind of repeat ourselves here, but I think it's important. So we're reflecting over the x-axis when the whole function is negative. So we get x negative y. And when the x changes, you reflect over the y-axis. And again, for a graph to be symmetric with respect to the y-axis, the point negative x, y must be on the graph wherever there is an x and a y. And for it to be symmetric with the x-axis, the point x negative y must be on the graph wherever there is an xy. And the graph of an equation is symmetric with respect to the y-axis if the replacement of x with negative x results in an equivalent equation. And the graph of an equation symmetric with respect to the x-axis if the replacement of y with negative y results in the equivalent equation. So the same answer. I said here that if you're looking for symmetry with respect to an axis, if you replace your x with negative x and you get the same answer, then you have some symmetry with respect to the y-axis. All right, so let's do some examples. So it says to test for symmetry with respect to the x and the y-axis. So let's go up here and let's replace our x with a negative x. So we get y equals negative x squared plus 4. So y equals, well, a negative x squared means negative x times negative x, which is positive x squared plus 4. Since these two are equal, then we have y-axis symmetry. All right, and let's look at B. Now we're going to replace the y with a negative y. So now we have x equals negative y squared minus 3. X equals negative y times negative y is y squared minus 3. So these two are equal. So now we have x-axis symmetry. All right. Keep in mind when the y is squared that it is not a function though. All right, now here we have the x squared and the y squared. If I plug in just the x squared, the same thing's going to happen as it happened here. And if I replace the y squared with negative y squared, the same thing's going to happen. So that means if I replace both of them, I get x squared plus y squared equals 16. So this is x and y-axis symmetry. Also, just for visuals, when you have y equals x squared plus 4, you are talking a parabola. And when you have x equals y squared, we have this. And when you have x squared plus y squared equals a number, you have a circle. So now let's look at this one. So let's plug in a negative x. So if I did negative x plus y equals 4, that gives me negative 2x plus y equals 4, not equal. So there is no y-axis symmetry. So try it with the y. So now we got 2x plus negative y equals 4. That's 2x minus y equals 4. So now we look at this, and these two are not equal. So there is no x-axis or y-axis symmetry. No x or y-axis symmetry. Now, what about respect to the origin? Now, the graph of an equation is symmetric with respect to the origin if the replacement of both the x and the y at the same time results in an equivalent equation. So a circle would be symmetric with respect to the origin. And this example here is just that. So we're not going to do that one again because you can see it right there. All right, now what about y equals x cubed? So if I do negative y equals negative x cubed, negative y is going to be negative y, And then I've got negative x times negative x times negative x, which is negative x cubed. Now, I know it doesn't look the same, but since both are negative, then that means if I divide by -1, they'll both be positive. Now I can see that this and this are equal, so this is respect to the origin. So we're going to say origin symmetry. It says, is a graph that is symmetric with respect to both the x and y axis automatically symmetric with respect to the origin? Is a graph that is symmetric with respect to the origin automatically symmetric with respect to either axis? If it's symmetric to both, then it is symmetric to the origin. So if it is symmetric to both x and y axis, then it is symmetric to the origin. All right. So the summary says if y is replaced with negative y, then you have x-axis symmetry. If x is replaced with negative x, then you have y-axis symmetry. And if x is replaced with negative x and y is replaced with negative y, then you have origin symmetry. So a graph symmetric with respect to the x-axis does not represent a function. It does not pass the vertical line test. So if I were to draw those vertical lines through here, you would see that it's touching your graph twice, where this one does hold true and this one does hold true. Now, even in odd functions. All right, so a function is called an even function if, when you replace x with negative x, you get the same answer for all x in that domain. And this would be symmetric to the y-axis. A function is called an odd function if you replace x with negative x, and instead of getting the same answer, you get the opposite signs for everything, then this is respect to the origin. So let's just see if they're odd, even, or maybe neither. So the first thing we're going to do is we're going to replace all the x's with negative x. So I get 8 times negative x to the 4th minus 3 times negative x squared plus 1. So a negative to the 4th power is going to be positive. So this is 8x to the 4th. A negative to the 2nd power is going to produce a positive. So we see that when we replace the x's with negative x, we get the same thing. Therefore, this is an even function. So now let's try this one. So f negative x is 6 times negative x cubed minus 9 times negative x. So we get 6, and that's going to be negative, negative, negative is going to stay negative. So this is actually going to be negative 6x cubed, and a negative times a negative is positive 9x. So now what I see is that I started with a positive 6 and I have a negative. I started with a negative 9 and I have a positive. So since both signs changed, then that means when I replace x with negative x, the whole function changes signs. So this makes this odd. And you can go over here and test it. So if I put a negative in front of the whole thing, distribute the negative sign, distribute the negative sign, and you can see that when I replace my x with negative x, the whole thing becomes negative, therefore it is odd. All right, let's try this one. So I'm going to plug in a negative x. So I get 3 times negative x squared plus 5 times negative x. So 2 negatives make a positive. Positive times a negative is negative. And then if I, put the negative out front just to test, we get negative 3x squared minus 5x. So I see that this is not the same as this. This is not the same as this. So this is neither. It is neither odd nor even. A function defined by a polynomial in x that only has even exponents, including the case of x to the 0, which is understood to have even exponent 0, it will always be an even function. And similarly, if there are only odd exponents, then the function will be an odd function. All right, so let's talk about translating a graph vertically. So translating, we're talking about sliding up and down. So translating vertically, so we're talking slide up or down. All right, so they give us this absolute value of x minus 4. So what we're going to do is we're going to choose some x values, and we're going to do the absolute value of x, and then we're going to do the absolute value of x minus 4. So I'm just going to choose some positives and some negatives. So the absolute value of negative 2 is 2. The absolute value of negative 1 is 1, 0, 1, and 2. All right, now plug in and add, and subtract 4. So now I've got 2 minus 4, which is negative 2. 1 minus 4, which is negative 3. 0 minus 4 is negative 4. 1 minus 4 is negative 3. And 2 minus 4 is negative 2. So let's plot both graphs. So negative 2, 2. Negative 1, 1. 0, 0. 1, 1, and 2, 2. So this is our f of x. And then we've got negative 2, negative 2, negative 1, negative 3, 0, negative 4, 1, negative 3, and 2, negative 2. So now we have this graph. So what we have is the exact same picture, we just shifted it down 4 because this number right here is telling you to shift it down 4. So this is a vertical shift down 4. All right, so how does the graph in example 6 compare to the basic? It's a vertical shift down 4. Now, vertical translations. So given your g of x, then you take your original function and you add c, where c is a real number. So every point on the graph, there will be a corresponding point. So your x value will stay the same, and since you're moving it down, because notice our x value stayed the same, but we moved down 4 each time. So this would be your y value plus your c value. If your c is negative, then it would be minus. And the graph of g will be the same graph, but translated up if c is positive and down if the square root of c, the absolute value of c is negative. The graph of g is a vertical translation of the graph of f. So a vertical translation. All right, well, let's look at a similar graph, but this time the negative 4 is inside. So this is going to be a horizontal slide, okay? Because remember, when you change the function by multiplying by a negative, it affects the y values. If you add a number to the end or subtract a number from the end of your function, it changes your y values. But if you put it with the x, then it changes the x values. So let's look at, so we're going to do the graph again. So we have the absolute value of x, and now we're going to do x minus 4 absolute value. All right, so I'm going to choose some negatives. Actually, I'm going to do 4 and 6. And the reason is because I want to try to get it as many points as I can so that I can see a full picture. So this is going to be 2, 1, 0, 1, 2, 4, 6. And then this graph is going to be negative 2 minus 4. So negative 2 minus 4 is negative 6. The absolute value of negative 6 is 6. And repeat that process. Negative 1 minus 4 is negative 5. So that's 5. 0 minus 4 is negative 4. So that's 4. 1 minus 4 is negative 3. So that's 3. 2 minus 4 is negative 2. So we get a 2. 4 minus 4 is 0, and 6 minus 4 is 2. So what I was trying to do is to make sure that I get a 0 in both columns. All right, so I'm going to plot the first one. So we got negative 2, 2, negative 1, 1, 0. So it's kind of the same graph that we did a while ago. So that one should be familiar. And then I'm going to plot the next one. So now I've got negative 2, 6, negative 1, 5, 0, 4, 1, 3, 2, 2, 4, 0, and 6, 2. So what I wanted to do was to make sure I had enough points so that I could plot the whole thing. I wanted to get both sides of that 0. So now you can see that we took this point, we went 1, 2, 3, 4. So we added 4 to the x-axis. So how does the graph compare to your basic function? So this is the basic function, and it shifted right 4 units. Every single point. So, and that's what this is going to tell us, that given your function, you take your function, so you take your original function and you subtract whatever number c is from every x value. So now you're going to have x plus c y for every point. Because here, if it says x minus, well, if I subtract a negative, then it's positive, and so on. So the graph of g will be the same as the graph of x, but translated to the right. So if you're looking at, remember when it's attached inside those parentheses, everything is opposite when you're dealing with the x-axis. And to the left, if you have x plus c. So the graph of g is a horizontal translation. So if it is x minus c, we slide to the right, kind of sum it up. And if it says x plus c, we slide to the left. All right, so let's sum up our translations so far. So if you add or subtract a number at the end of your function, that is a shift up c units. If you subtract a c from the function, that is a shift down c units. if you add C, this is a shift left. And if you subtract C, that is a shift right, C units. And that's because if you plug in a negative here, a negative makes a positive. So how to explain how to determine the direction and magnitude of a horizontal shift of a function. So I put if x plus C go left, if x minus C go right, think backwards. All right. So what if we have more than one? Okay. So we have an x out front. So that x out front, that is going to be a x-axis reflection, or reflect over the x. Okay, so this negative sign here will determine that. This plus 3 in here is going to be a horizontal shift right, or sorry, left. Horizontal shift left. And then this plus 1 is going to be a vertical shift up. So if you think of a reflection over the x-axis, that's going to be negative xy. A horizontal shift left, that means you are subtracting 3 from all the x values. And a vertical shift up, x is staying the same and all the y values are changing. So that's what's happening. That's what is happening to the original function of the absolute value of x. So if you knew this graph here, then you would change your x values, change your y values, and so on. So let's do a little table here, just so we can kind of see. So now we've got negative x plus 3 plus, whoops, that's not, plus 1. All right. So I'm going to choose some positives and negatives so that I can get on both sides of the graph. All right. First, so we got 2, 1, 0, 1, 2, 3. So I'm going to graph that. So negative 2, and I'm going to enlarge this a little bit so I can see it better. Negative 2, 2, negative 1, 1, 0, 2, 3. I've kind of gotten comfortable with that one. It's kind of repetitious. All right, now let's do these numbers. So we have the negative out front this time. So negative 2 plus 3 is 1. Then we have that negative out front plus 1. So that's going to be a 0. Now plug in the negative 1. Negative 1 plus 3 is 2 with the negative out front. So now I've got negative 2 plus 1. So that's negative 1. And 0 plus 3 is 3 with the negative out front is negative 3. Negative 3 plus 1 is negative 2. Plug in a 1. 1 plus 3 is 4 with a negative 4. Plus 1 is negative 3. 2 plus 3 is 5. With a negative out front makes it negative 5. Negative 5 plus 1 is negative 4. And then we've got 3 plus 3 is 6 with negative 6. Negative 6 plus 1 is negative 5. So now I'm going to plot those points. So now I've got negative 2, 0. Negative 1, negative 1, 0, negative 2, 1, negative 3, 2, negative 4, 3, negative 5. So notice what we have is a line going this way. So what we need are some numbers on the negative side. So what have I plugged in? A negative 3. Negative 3 plus 3 is 0, so that would be 1. So that would be negative 3, 1. So negative 3, 1. All right, well, what about a negative 4? Negative 4 plus 3 is negative 1, and the square root, or the absolute value of negative 1 is 1, but we have the negative sign out front. So now we've got negative 1 plus 1, so we get 0 again. So we're going back down here to here. So now we can see that we're coming back this way now. So what you should see is we reflected this graph to where it's upside down. Then we shifted it left, and then we shifted it up 1. So we went from, we took this and we flipped it up, then we moved it up, and then we moved it left. So that would be exactly what we did what did happen over here using the actual numbers. All right, so now let's look at the absolute value of 2x minus 4. Well, the first thing I'm going to do is factor out a 2 because you are able to do that. So I'm going to factor out a 2, so this is going to be, well, for some reason this thing is not cooperating. So we've got 2 absolute value of x minus 2. So now I've got a 2 out front, which tells me that's going to be a vertical stretch. So we have a vertical stretch. So my y values are going to get bigger. And then I'm subtracting 2 from all my x values, so this is a horizontal shift to the right. All right, so if I create my table here, so we have x, absolute value of x, and 2 absolute value x minus 2. All right, so let's look at creating a table for this function. So if we choose some x values, I'm going to choose just some even numbers. So let's look at negative 4, negative 2, 0, 2, and 4. And you can choose whatever. I try to keep them small. All right, so the absolute value are all positives. All right, so now take these values and plug them into the equation. So we get negative 4 minus 2. So that's negative 6. So 2 times 6 is, oops, let's see here. I think negative 4 minus 2 is negative 6. The absolute value of negative 6 is 6, and 2 times 6 is 12. All right, and then we're going to do the same thing this time with negative 2. So now we got negative 2 minus 2, so that's negative 4, and the absolute value of negative 4 is 4, and 4 times 2 is 8. 0 minus 2 is negative 2. The absolute value of negative 2 is 2, and 2 times 2 is 4. So you should notice what's happening over here, that each time it's decreasing by 4. So 2 minus 2 is 0, and 2 times 0 is 0. 4 minus 2 is 2, and 2 times 2 is 4. So you start going back up. So what I'm going to do is I'm going to graph the first one here. Let's slide this over and up a little bit. All right, so we got negative 4, 4. negative 2, 2, 0, 0, 2, 2, and 4, 4. So there is our generic function there. And then the next one is negative 4, 12. So it's going to be up here somewhere. Then we got negative 2, 8. Negative, 0, 4. 2, 0. And 4, 4. 4, 4. So what you see is, you get an idea. So you can see that we did a horizontal shift of 2. 1, 2 is our horizontal shift. And we have this vertical stretch of 2. So notice that the number, so if we're using the same x value, the y value got bigger, so that was a vertical stretch. All right, so let's move on. We're getting close to being done with these. These were a really long set. All right, so here we have negative 1/2 x squared plus 4. So this negative sign here, this tells me it's a reflection, reflect over the, so reflect over x-axis. This 1/2 here, this tells me this is a vertical shrink by 1/2. So a vertical shrink. And then this piece right here tells me there's a vertical shift up. So we're going to take our f of x, just our regular f of x is just x squared. And we're going to flip it over the x-axis. We're going to make it skinny, and we're going to move it up. So let's create our table with these so that we can numerically and physically see. So we have x squared, negative 1/2 x squared plus 4. All right, so since we're dealing with a half, I'm going to choose even numbers for my x values. So when I take half of something, I'm not left with another fraction or decimals. So I'm going to go negative 4, negative 2, 0, 2, and 4. And like I said, you can choose whatever x values. Just try to be mindful when you do to choose some that's going to make your problem a little easier. All right, negative 4 squared is 16. Negative 2 squared is 4. 0 squared is 0. 2 squared is 4, and 4 squared is 16. All right, so now we're going to take half, or we're going to square it. So we got the negative 4 squared, which is 16, and then we're going to take half, which is 8, and then we have the negative sign. So we have negative 8 plus 4, so that's negative 4. And I'm going to go through and do that same process for every number. So we know negative 2 squared is 4. So this piece becomes 4 because that's here. Half of 4 is 2. So we got negative 2 plus 4. So that's a 2. 0, well, if I plug in 0 here, it all cancels out and we get 4 again because we just have that one piece left. All right, now if I plug in 4, so this piece right here, the x squared is 4, half of 4 is 2, and it's negative 2. So negative 2 plus 4 is 2 again. And then plug in that 16 again. Half of 16 is 8. Negative 8 plus 4 is negative 4 again. So let's graph both of these. So negative 4 and 16 is way up here somewhere. Negative 2 and 4. 0, 0. 2, 4. And 4, 16, so it's up here somewhere. So this is an x squared, so that's going to be our graph of a parabola. So it's a curve, not, it's a, see if I can get that to look normal. All right, and then our next set is negative 4, negative 4. So we got negative 4, negative 4, negative 2, 2, 0, 4, 2, 2, and 4, negative 4. So now we've got this graph. And I wished I had, let me get rid of some of this. Wish I could draw it more exact. But the negative sign, we reflected over the x-axis. So we took our purple graph, we flipped it. A vertical shrink, our y values got smaller, and a vertical shift up, we went from here to here, so we did shift it up. So there is a visual image and numeric image of both of those things happening. I really think that if we didn't have to graph so much, that it wouldn't take near as long to do this, but graphing takes forever. All right, here we have graphing translations and reflections on a given graph. So we're going to take this image here and we're going to do this to it. And we don't need to even know what the equation is. I just know that whatever the equation is that gave me this picture, I'm just going to add 3 to all of those points and regraph it. So I'm going to take this negative 4, 0, and we'll go 1, 2, 3. I'm going to take this negative 2, 2, 1, 2, 3, and just shift everything up. 0, 0, up 3. This is 1, negative 4, 1, negative 4, 1, 2, 3, shifted up. And 0, 3, 0, 1, 2, 3. So now I've got, and there you go. So that's all the main thing is that you know that you just need to take it and shift it up 3. Now this time, instead of the the 3 being at the end, it's inside the parentheses. So x plus 3 means you're moving left 3. So now take all of these points and go left 3. So negative 4 goes to negative 7. This negative 2, 2, 1, 2, 3, 0, 0, 1, 2, 3. So there's that hump right there. And then we've got the 1, negative 4, 1, negative 4, and we're going to go 1, 2, 3. So there's that part. And then 3, move it left 3, and there is that piece there. So when it's inside the parentheses with the x, it's a horizontal shift, and it's always opposite of the sign. All right, let's see the next one. So now we're going to take that same picture and we're going to go right 2 and up 3. So we're going to go to the right 2 and up 3. So we had the points negative 4, 0. We have negative 2, 2, 0, 0. 1, negative 4, and 3, 0. So those are the 5 points that give us that picture. So to every x value, you're going to add 2. So add 2, you get negative 2. Add 2, you get 0. Add 2, you get 2. Add 2, you get 3. Add 2, you get 5. And then to all the y values, you're going to add 3. 0 plus 3. 2 plus 3, 0 plus 3, negative 4 plus 3, and 0 plus 3. Those are your new points. So if you can start with your original points, you can get your new points just by knowing what's happening with your translations. So negative 2, 3, 0, 5, 2, 3, so there's that first hump, 3, negative 1, and 5, 3. So it goes, and there's the same picture. So we still have our original points over here, so I'm going to use these original points and try not to zoom out too much. Now it says to do a vertical flip. So that means that if you are turning your entire function negative, that was the reflection over the x-axis. So this time you're going to take it from up here, so every point up here, and it's going to reflect to down here. If it's here, it'll reflect up this way. So that means that your x values are going to stay the same, but your y values are going to change, okay? So looking at your original points, your x values are going to stay the same. So they're going to stay -4, -2, 0, 1, and 3. And all of your y values here are going to be opposite. So that one's not going to change. That one will be -2, 0 stays 0. -4 becomes +4, and 0 stays 0. 0 is always good. It never changes. So now we got -4, 0. We got -2, -2. We got 0, 0. We got 1, 4. And we got 3, 0. So all you did was flip it upside down. So this is a reflection over the x-axis. So here is our summary. So assume that a is greater than 0, h is greater than 0, k is greater than 0, and in comparison with just your graph or any function f of x, if f of x plus k, you translate up k units. If it's minus k, you translate down k units. If it's x plus h, you translate left h units. And if it's x minus h, you translate right h units. The graph of a times your function is a vertical stretch. As long as a is greater than 1, and it is a vertical shrink if a is between 0 and 1. Now, if your a is inside the parentheses, then it is a horizontal stretch. As long as a is between 0 and 1. And it is a horizontal shrink if a is greater than 1. And if you put the negative sign in front, it is reflected over the x-axis. And if the negative is attached to the x inside the parentheses, it is reflected over the y-axis. So what I like to do is I like to think of these as what you're going to do. What you do to one point, you have to do to all of the points, not just one. So I think of this as x stays the same, and I'm going to add something to all my y's. Here, this would be x stays the same, and I'm going to subtract from all my y's. This one would be x minus h, and now y stays the same. This would be x plus h, and y stays the same. The vertical stretch is x stays the same, and it's a times y for the stretch, and for the shrink, x stays the same, and it's 1 over a times y. Whatever that number is, of course. Your horizontal stretch is multiply 1 over a times your x value, and y stays the same. And for the shrink, it's a times x, and y stays the same. Reflect over the x-axis, x stays the same, and y negative. Reflect over the y-axis, negative x, and y stays the same. So if you think about what's happening to the points, that's kind of what's happening, so that you get an idea. If you know what one point is, if you can perform these functions on that one point, you do that same thing to all of your points. All right, I am going to upload this and get started on the next one. Have a great day.